Now the next example I want to go after, and maybe the last example, is what about tertiary haloalkanes? If you are a tertiary haloalkanes, a nucleophile will replace your halogen, but it will go through SN1, substitution nucleophilic unimolecular. And we have to talk about this one. Where does it come from? So if you do a kinetic study, and if you have two reactants, if you look at experiment 2 versus experiment 1, concentration of nucleophile is constant, but I doubled the concentration of the halogen, the rate got doubled. So the rate is saying from experimental data is equal to K times the haloalkane, which is a tertiary haloalkane, is 2-methyl 2-bromo 2-methyl propane, first order. Now if you look at experiment 1 versus experiment number 3, I held the concentration of haloalkane the same, but I changed the concentration of cyanide by 4-fold, 4 times. The rate did not change. So that says the nucleophile, in this case cyanide, is 0 order. So I really don't have to show it. If it's independent of the nucleophile, what is the mechanism? And that's where elementary steps, rate determining step, and all those information come back to life. So the mechanism is involving 2 steps. Step 1 is simply your haloalkane. That will go through a heterolytic fission. Bromine's covalent electron goes away from it. This is a slow step, so we call it rate determining step. And it will produce a carbocation, and remember this is heterolytic fission. It will produce an anion and a cation. Your cation is known as carbocation, extremely stable, and it will produce bromide. And this is, since it's rate determining step, its immediate rate is K times your haloalkane, which is exactly the same as the experiment. So it's good enough to justify why it's first order with respect to just the haloalkane and independent of cyanide or your nucleophile. The second step is fast. You have your carbocation with a positive carbon ready to be attacked by the nucleophile, cyanide in this case. You have to show your Cowley arrow one more time, so I put my cyanide, lone pairs. The lone pairs are going to attack the positive carbon fast, so the rate is not changed due to its concentration, and it will give you CH3, 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 and a new organic homologous series of nitrile comes to life. So remember, this is a nitrile family, and you can add more hydrogens to it and make it into amine. So this is SN1, so from now on you have to remember tertiary goes through SN1 as substitution reaction.